Tonight we're hearing from one of our members, Eddie Thompson. And of course I forgot his call sign. Interestingly enough, it's right there. And for all of his details, you can read the article in the e-news for a full, and he'll give you some information tonight. Please welcome Eddie.
Okay. I feel like a ventriloquist. Okay. Well, good evening, everybody. A little bit about me. Well, I'm not from around here.
You're from South Jordan.
But I am a southerner. But I'm from southern England. Not too far from cities you may well have heard of. You've probably heard of Windsor, where the castle is, and you've probably heard of Stonehenge. I come from a little town of probably about 15,000 people that nobody has ever heard of, so I won't mention it. But I've been interested in ham radio since I was about 12. It works. And originally I came introduced to the hobby through a school friend of mine, whose father was a radio ham. And I was lucky enough to spend one Halloween evening at my friend's house. We were celebrating Halloween, and his father was operating ham radio, talking to a gentleman in Canada, Victor Echo 3 Papa Tango, his call sign. And I was listening to the conversation, heard my name called back to me on the radio, said hello, and sent me a QSL card, and I was hooked for life. But it took me a little while, so I was putting apart my mother's transistor radios, anything electronic. But finally, I was licensed first of all when I was age 15 as Golf 6 Kilo Charlie Delta, and then about a year later I got my Morse code, 12 words per minute, and got the call sign G4SQZ, as I would say back home. I moved here in '95 in the telecommunications industry. Took my exams down in Jonesborough. A friend of mine from the Kentucky Club at the time took me down there. Got my call sign in '97. And I've generally liked DXing when the bands are open. A little bit quiet right now, so maybe I do more FT8 these days. Local repeater work, of course, on the NF4GA and a few other repeaters locally. And then AMSATs, and we'll talk about that in a moment. And married to XYL Heather, who encourages me with the whole hobby. She will get on the roof and will help me mount the antennas. She will throw lines up in the trees. And she allowed me to put ham radio in her truck, so so everything is good. Everything is good. Only a brother. First of all, how many of you have actually done amateur satellite work, either listening, working? Okay. And how many use maybe antennas mounted on the house in a fixed position? Okay, a few of you. And then, how about going out into the out to the yard and doing the hand thing? We'll talk about that. How was that? Yeah. And then, who has dedicated azimuth elevation equipment? Sort of, probably more upstream from this. Okay, very good. So, quite a lot of interest. So my satellite experiences, we talked about, well, basically the 1980s. Back in those days, Oscar 9 was going around. It was from the University of Surrey in the United Kingdom, and it used to broadcast its telemetry by voice by a new system called Digitalker. And that was quite fun to listen to because you didn't have to decode it. You could listen to this thing talking to you. So I remember listening to that in my late teens. And there was also Oscar 13, which had a really elliptical orbit, and it would hang in the sky for like 2 or 3 hours, keeping on their skies. But it was very good. You could hear countries from all around the world on Oscar 13. And then more recently, I would say maybe the last 2 or 3 years, I kind of got interested in decoding weather satellites. And it's kind of where the satellite interest kind of started to bloom for me. Obviously listening to the old analog NOAA satellites. And then more recently, a couple of Russian satellites, these Meteor M2, which broadcasts a semi-high definition picture. You can see one in the background here. This is one I took last year back in September when Hurricane Florence was over in the northeast. So at that time I was using some antennas we'll talk about later on that were just bounced from the top of the house. They were omnidirectional, right-hand circular polarized Homebrew. So that's kind of where the satellite bug came from. And then I got interested in field day a few years ago and got involved with some of those activities. And where's Dave? K4UW. This is the man that inspired me to build this thing. Dave, here, right, give him a hand because... So, here's the story, this is how this started. How many points do we get for one contact on satellite, Dave?
100.
100 points. You get 100 points, so you can either work 100, if you're doing it the regular way, you can try and work 100 contacts by SSB for 100 points, or you could do 50 contacts on CW for 100 points, keep me honest, or you can work one contact on satellite and get 100 points. And Dave recognised this, and remember we were trying to get satellite contacts for field day, and using the old Armstrong method and varying degrees. And there's a lot to do. You really got to know, well, what time is the satellite coming up over the horizon? What's the acquisition of the signal time? When is it going to go down below the horizon, the loss of signal? Which direction is the satellite? Where is it whereabouts is it from the horizon? Which direction is it? Oh yeah, what's the frequency you're going to listen to? Oh no, by the way, the frequency changes as this thing moves over you. So you've got to keep changing the frequency on the radio to track the Doppler shift. What mode is it? Is it upper sideband or lower sideband, depending on if you're trying to work a contact on with a transponder, and you're trying to hold the radio. You have a pair of headphones on, probably hold the microphone, trying to have a piece of paper. I mean, I'm exaggerating a little bit, but even if it's all on a table in front of you, there's a lot to do. I tried working some of the FM satellites back last summer, and by the time you do all this, you hear somebody, you call them, and the satellite's moved, maybe it's faded, and you're turning around, and basically before you know it, 6 minutes have gone by, and maybe somebody called you back, and you're calling them, they don't hear you, or you can't remember their call sign. It's just a lot going on when you're trying to do this manually. Not to mention, of course, in the middle of summer, it's 90 degrees, it's humid. I've walked off the deck in the house. I'm now in the backyard trying to get away from the trees, and then the grass is up here in the backyard, and I'm getting eaten by mosquitoes. Like, oh no, wait, I'm going in. So it's a lot to do, and so I knew there was a better way of doing this. I knew I wanted to find a way for getting these bonus points quickly and easily for field day, and it was an inspiration. Well, okay, I knew that you can buy commercially made antenna rotators for azimuth and elevation. So just for those, azimuth is in this plane, from 0 to 360, and elevation is in the vertical plane. So an antenna that will move at the same time and follow this, an antenna controller, excuse me, they're commercially available. So, I didn't want to spend thousands of dollars on a azimuth elevation controller to find out. I had no clue how to work satellites. If I was going to do it, I was going to do it fairly cheaply, at least to start with, before I upgraded. So here's some commonly available. These ones are high gain. I can't remember the type numbers, but these range between $1,600 and $2,100 for just for these azimuth elevation. They're very expensive. There are some more medium cost options available. Yaesu does one for $750. They're in the range $750 to $800. There's another one that I saw at Dayton this year, made by this company called Portable Rotation. where it had two separate boxes that moved. I think somebody else showed me something similar. But it was $800, and actually it did really look very mechanically robust. It looked like it would, if you kicked it, it would fall over and break apart. So I thought, well, there has to be a better way. And so I did what everyone else does. I went and looked on the web for what's out there. Well, hang on, before I get there. So I did find something. I did a lot of searching. I found things where people experimented with various designs, and these designs either fell over on the floor or they stalled. There's always some problem with them. But I did find something. We'll talk about that. We were talking before about using these omnidirectional antennas. Does anyone who does satellite use the egg beater antennas? Okay. Yep. Yeah. One large one for 2 meters and a small one for 70 centimeters. It's circularly polarized, so it can see in all directions, and it's should be right hand. It can be right hand or left hand circularly polarized. You can swap it. So basically, it eliminates the satellite fading. These work pretty well, and you can find the design. There's a link here. If you click on that link, you can go to the designs that were published by K50E. They don't look like this, but they're very good. I use a 2-meter version just for reception for the weather satellites. It works very, very well. You can make it probably for like $25 or something. So that's an option, but kind of limits you maybe to satellite visibility maybe about 30 degrees in the sky, because once you get down the sides, it fades very quickly. But not a bad solution. But I wanted something where I could use an antenna with a bit of gain, like this Yagi here, and point it in the right direction. So eventually, my search took me to the Australian School Amateur Radio Club, SARC, and there were 2 radio amateurs, Julie and Joe, who were running these fun educational science, technology, engineering, math, lunchtime enrichment activities for these students in Australia. And as you can see, this looks sort of familiar, right? So they actually published 3 designs, actually. There were 2 like low, what's the right one looking for? They were like very light, like this, and there were other designs that were more robust, more heavy duty. And I chose this Mark 1 version, and we'll talk more about the details, but essentially the Mark 1 version was slightly simpler in the electronics, a little bit more efficient electronics, a little less wiring, so I selected that design. And this whole design, give or take, excluding the antenna, that's everything in the box down here through to the Raspberry Pi controller, which you don't see here, was less than $150. I started the project this time last year. I started searching the web for this design, which I came across, and started building it. And I finished this project actually on Christmas Eve last year. And I didn't get a chance to test it because it was raining. Remember how much rain we had last year? It was rain, a wet summer. So I had to wait until, I want to say February or March this year to try this thing out. We'll talk about the results of that. A couple of other important things. Julie and Joe, they will provide you all the details. You go to their website. This is the website. They'll show you the circuit diagram, all not excruciating, but all the detail you'll ever need to build this, if you're so inclined, and all the bugs and the gotchas, and watch out for this, and make sure you do that, all included in this whole published online. And also there is some software that you need that translates the commands coming from the computer to the controller, that they'll also provide you free if you ask them nicely, and they give you all the free encouragement that you need to do that. And they'll also publish a nice picture of your antenna if you build one on their website. And I think to date they have had close to 400 people that built these as a result of this design. I think what they ended up doing was actually they took this further on and ended up creating a and an Android version of the controller that they ended up, I think, selling, but they still provide all the details for these designs that we're going to talk about here. Find my drink. Okay. So let's talk about controller design. Most of the antenna rotators that we tend to see on rooftops, for example, you have to make sure you set up the rotator point. If you set the rotator point north, you have to make sure the antenna point's north, and then it's a relative reference from there. Okay, so if you don't set it up properly, a classical antenna rotator won't point in the right direction. You have to point it in the right direction, and it's all relative. The SARC design that we're going to talk about here uses an electronic sensor. It's an electronic compass, and it the absolute direction that the antenna is pointing to, both, not just at the azimuth, but also the elevation. It's absolute. And we'll talk about when you set this thing up, when you first plug this thing in, it'll automatically find true north and it'll stay there. And you can pick up the tripod, turn it round, and the antenna will try and move back to due north, or you can tilt the whole thing and it'll try and find its original level. So you don't have to do anything in terms of setup. We'll talk a little bit about the calibration of this little device. It was an interesting find. I was looking on the web this week as I was preparing for the discussion, the talk, and there's some activities that they said you need to do that I actually found out you don't. So, and by the way, this device here, that's this little tiny thing right here. You know, if you can see it, that's the device right here. That's the E-compass. It's actually the accelerometer. We'll talk about that in a moment. So that's the key thing about the design of this, is it uses this E-compass, this little microcontroller. So okay, I think you see here. By the way, you notice no secrets. There is actually electronics in this box. It's not full of air. So yeah, you have the tripod. This is actually a pile speaker stand, which I picked up at Dayton for about $18, brand new in the box. And of course, the actual antenna controller is the top part of this. We've got the E-sensor connected on a short cable. The reason this could be permanently connected here, but the reason I don't connect it permanently and it's attached by Velcro is because I actually want to remove this antenna so I can make this whole thing portable. So there's a reason for that, and it works very, very well with the Velcro, and I'll talk about that in a moment. So inside the box, we'll see more about this. There's a microcontroller that computes the azimuth and elevation based on the actual. It determines what direction the antenna is currently pointing to. It then controls there's two small DC motors. They're 12-volt motors. They're about 0.6 revs per minute. Little reducing worm drive, but very high torque. So it's got the strength to move this antenna. And the whole thing is controlled by a USB. You can drive this thing with a laptop running satellite software, or in the case for me, I run it with Raspberry Pi 3B. But you've got the USB connection there for the computer control. We'll talk about a bit later on. I choose gpredict for the satellite control, but there are other programs that you can use, and we'll cover that here in a moment. So, try not to get too technical, but I want to give you guys an overview of this. So here's the whole thing, and I've got the prices here. So I have a Raspberry Pi 3B computer running Raspbian. That's about $35 from Target. I think if you buy a laptop, they're significantly more if they're running Linux. So the Raspberry Pi talks to the microcontroller inside this box via USB. The microcontroller takes the commands coming from the Raspberry Pi 3B, and one of them takes the input from the E-compass for where is the antenna pointing, and the other one says this is where I need to point the motors to. One for azimuth and one for elevation. And the 1B design, the Mark 1B design, uses this dual stepper motor driver. In the 1A design, there are two separate motor drivers, one for each motor. Why have two cards? I just have one card and make it simpler, and it actually fits in the box quite nice. So that's why I chose the 1B, because it uses one single card to drive the stepper motors. These are all Arduino devices. Those are, they're cheap open source electronics that are easy to use. You can see the prices of these things are, $7 for the microcontroller, $7 for the E-compass. You can find them for less than that, and maybe 10 bucks each for the motors. So it's more the price as the antenna and to the other items. So here's the circuit diagram, just to give you an idea. More just to kind of show you that this is straight from the website. What I want to kind of focus on here is sort of how this sensor is mounted on the antenna boom. There's a specific reason why it's mounted like this, is because we want to put the flat side with no electronics against the boom of the antenna so it can lay flat. However, that doesn't line up with the way that this device is actually configured. You'll see at the moment, but for example, you'll see that the x-axis on the device points this way, but in the way that it's implemented on the software is its x is here. And what they do is there's basically a translation that's done with the device and some mathematics so that you can actually mount this thing flat and point it along the direction of the boom. Right. So here's the layout. It's fairly straightforward. There is no milling. The only thing you need to do is drill accurately for the positions of the stepper motors. There's some little washers in here. You can see there's like some little ridges here in the box, and you just need to use some washers to straighten out the motors. I think I did a little tiny bit of filing here, but there's minimal mechanical work other than just drilling holes in the right place and the right size, I would say. You can see the USB connection coming in here to the microcontroller. There's a couple of little capacitors on here to reduce the noise from the interface. And the rest of it's the motor controller. And one is labeled azimuth, which is this one. And this one is elevation. Standard USB. Oh, and shielded cables, of course, to minimize any noise either generated by the device or noise that it will actually detect. And you see there's a single grounding point there. Everything is grounded to a single grounding point here. And when you look in the article published by SARC, they're talking about using telephone wire to connect, the sensor and everything. This is all shielded cable. So RF 101, everything is shielded, including the USB cable, even the power. No, not the power cable, but so. And that means that when you're listening to a satellite, you want to keep the noise level stays way down, because the electronics are going off and on all the time. They do create noise, so if you don't do this, you'll then end up with more noise and you won't be able to hear your satellites. So very key point. So I wanted to talk about this E-compass. This is a very busy slide, but there's a great simple answer to this. So it's a 3-axis accelerometer magnetometer. That means basically it's an accelerometer. It knows it can sense acceleration. It can sense the force of gravity, and it knows where it is. We said we need to mount the sensor flat on the antenna. It has a specific direction it points in. You'll see here, the actual device itself is set up so X is in this direction, Z is coming out of the page, and Y is over to the left. But the way we want to use it is actually the way I've shown you here. So this would be the boom pointing in this direction. If I go back to the other picture, so Y is along the length of the boom, along here, and then X is across the top of the boom, and Z is kind of coming, hard to do here, kind of coming out, in and out of the picture here. So there's some little conversions that the software does. You know, for example, here the X direction, the software translates to Y. The Y direction, the software translates to X, and so forth. Well, so the great thing is, we're going to say, well, who cares? And thank goodness for that, we don't care. As long as you mount this thing correctly on here, the software will do everything for you. There's all these calculations that, thank goodness, we don't have to think about. That's all included in the software that the SARC folks can provide us. The only thing I would say here is that I encapsulated this in epoxy glue so that it was electrically insulated, as well as it was, you know, it makes it robust. I would not want to put this in. I would not suggest even putting this in shrink sleeving. I would definitely encapsulate that in some kind of solid glue, which is what I did. The other thing is, it's just like any regular compass. You have to keep this thing away from anything ferrous, anything metal, anything with iron in it. So I think I had some correspondence from a few folks where they had the sensor right here, right next to the pivot point on the antenna. Well, there's metal screws behind here. That's not going to work. Another thing is, if you mount the sensor, say, right behind here or here, now you're in the path where you're in the RF, and your RF will get back into the sensor, probably. So for me, it was about a midpoint between the counterweight and the pivot point, and it works very well. So when you look on the SARC website, it talks about having to calibrate this sensor, and it's a process that uses the Earth's magnetic and gravitational fields, and no test equipment is required. Basically involves waving it around, kind of. Well, I'm going to talk about that because it's kind of interesting. But I discovered that, quite frankly, this device out of the box comes calibrated anyway, and good enough for ham radio use. I think, without going into the technical details, it talks about soft ion interference and this type of thing that causes the device to skew. For our use, we don't need to really calibrate it unless you've got this thing very, in some location that's got horrible magnetic, area or something. So chances are you could probably take this thing out the box, the e-compass, and just use it as it is. I did actually do the calibration, and I don't know what it was before, but after I did the calibration, when I pointed it in the direction I expected, it gave the measurement in that direction. So we talked about the software. It's provided by the SARC folks. So you send them an email, they will reply back with the software as an attachment. The software currently is called Rotator 6. It's code for Arduino, and it basically translates the commands coming from gpredict, which is what the software that you're using to control the antenna, into something that would actually allows the antenna to move. I say get this free from the SARC team. You have to install basically what's called an IDE, the Integrated Development Environment, which allows you to load the program, compile it. A couple of real main important thing here is when you get the code, you actually have to tell it which motor controller type we're using, because the software is flexible and allows for maybe 2 or 3 different types of motors and two or three different types of e-compasses, so you have to tell it which one you're using. You upload the code, and you're then ready to do this e-compass calibration that I said you don't really need to do, but I'm going to cover it because it's interesting. But the software is key. You can't, unless you want to write something yourself, you have to get the software, and right now it is currently free. And that, don't forget, this is the one that includes all of those calculations for all the math that will decode this e-compass. So, this calibration, something you'd only have to do once, and you have to take your time, and you have to do it carefully. You have to know your magnetic declination. That's the difference between magnetic north and true north, because when the satellite programs are calculating the position of the satellite, it's based on true north, not magnetic north. So the software has to know what that difference is. And here in where I live in Marietta, it's pretty much the same here. Is magnetic north is 5 degrees west of true north, and you basically just enter that into the software, and because it's west, you enter it as a negative number. So put the magnetic declination in as minus 5.17, and there's a little routine in the software that you start to run that gives you a whole bunch of numbers. So I can't. This chip is tiny. It's a tiny device on this, but I kind of want to show you this. Imagine this is the chip that's on. That's the actual accelerometer sensor. Imagine that's what that. Let me just show you the picture a second to make sure we. So imagine this Rubik's Cube is that chip. And imagine, this green face is X, and the red face is Z, and the orange face is Y. And basically, you have to take each of the 6 sides, and so in this case, the software is running. We've got this face here. And you have to basically, as the program works, there's a little piezo buzzer that beeps all the time until you've actually got the calibration correct. And so the calibration, imagine, okay, this orange line, this is a plumb bob, this is pointing directly down to the center of the Earth. You have to move the device around until such time you actually, the sensor aligns with that gravitational force. Basically, when these two things are, trying to show you graphically, when these two things align, the buzzer will stop beeping, and you'll know you've got the calibration correct, and you have to kind of do it again you basically sort of move it around until it stops beeping, and then if you imagine I have to turn it over to the other side very carefully, and I'd have to do the same thing, and I do that for all 6 sides until the software stops beeping, and I know I have the calibration, or at least I think I've got the calibration at that point. I say, you don't have to do this. The calibration is good enough. I subsequently read of the device from the manufacturer, but if you want to go the extra mile, this is actually kind of fun. So, but I did actually do that. And you might say, well, how do I know if it's calibrated properly? Well, it's pretty simple. Before you put everything in the box, imagine you have the laptop or the Raspberry Pi. It's connected to the microcontroller, and it's connected to the e-sensor. It's pretty simple. On the desk, put yourself a protractor on the desk. Make sure you point it to true north. Make sure it's away from anything metal or magnetic. And literally just put the sensor, point it north, and make sure that the numbers on the side say it's pointing north, and turn it round to the east and make sure it says it's 90 degrees, and point it round to the south, make sure it says 180. So basically, it's a sort of a common sense check, right? And you can point it in the direction. Just make sure that for the azimuth, it actually reads the direction you expect it to before you put it all together. And the same thing for elevation. I think I didn't have one of these. I can't remember what these tools are called anymore. It's like a square. Well, so, but if you lay the sensor on the table, it should show 0 degrees. If you point it vertically, it should show 90 degrees, and somewhere in between it should show 45 degrees. So, so there's a quick way of making sure that the sensor is giving you the right values. Do all of that before we even start putting this whole thing together in a box. And then that way we know that with confidence this device is going to point in the right direction, which it does. And then there are some other checks you have to go through once you've got it all built in here, but before you connect the antenna. For example, it says it up here, but if you point the sensor down, the antenna should go up. If you point the sensor up, the antenna should go down. It's negative feedback. If you take the sensor and move it to the left, the antenna should move to the right, and so forth. So some basic checks to make sure you have the wiring the right way around, because oh, by the way, the authors don't tell you what the polarization is of the motors. They just show connections of the motors. If I go back to that slide, doesn't say plus or minus on here, does it? Doesn't tell you. And I had to figure that out by trial and error. Luckily, in the article I wrote for E-News, I did put the polarities on there, just so you know. So we got the calibration set. And it's going in the right direction. Let's see that. So, put the whole thing together. You have no laptop connected to this device, but you power up the motors are powered up by 12 volts, by the way, which I have like a separate 12 volt power supply here. Right. And the microcontroller gets the 5 volts from the USB coming from the laptop or from the Raspberry Pi. But if you have this thing plugged into 12 volts and you plug in the USB, as soon as this device senses the power from the USB, the antenna will swing round immediately round to due north and point at the horizon as like a home position each and every time. If everything is working correctly. And as I said, if you move the tripod, so if you tilt the tripod, the antenna will try to move up. If you try and rotate round the tripod, the antenna will try to move back round to due north. So everything is ready at that point then to connect this device up to the G-Predict software. So how many of you here are familiar with G-Predict? Who's heard of G-Predict? Okay. Other alternatives, Ham Radio Deluxe you could use. It would also drive this. There's SAT PC32 is another one. I think Predict is a version of G-Predict, and Orbitron is just another freeware. But there's other variations. Yeah.
So, I mean, once the microcontroller is programmed with the code from the software folks, then all of these applications know how to interface
Yep,
with it?
I'll come to a whole diagram of the whole thing here in a few moments. Yes, basically. So we're using G-Predict because we want to track satellites of interest. We can either pick them manually from a list, or we can use the auto track feature. So originally when I started building this project, I used a PC. And one of the nice features about the protocol that we use to drive this is it gives us feedback. Not only can we tell this antenna which way to point, but the sensor will tell you where it currently thinks it is in relation to where you're telling the antenna to be, which is nice. So basically, I don't have apologies, I don't have a picture of it, but on G-Predict, the target, if you imagine you have a diagram, there's a little circle that shows you where you're planning to point the antenna, and the feedback is a little cross showing you where the rotator is in relation to where you asked it to go. So you usually ideally the crosshair should be in the middle of the circle, so you get feedback. It's really nice to know that the thing isn't lagging. Well, the feedback only works on a PC with G-Predict version 1.4. seems that all the other versions of gpredict that went after that have some problem with the, we'll talk about it later, but it's the protocol that gpredict uses to talk to the antenna is called EasyCom 2. And the feedback only works with gpredict 1.4. So I thought that's fine, but gpredict 1.4 doesn't have the auto track feature, which is really nice. You know, I think some of you saw this in the park. I can leave this thing and it'll automatically swing around and find the next satellite. that pass goes over and it'll swing around and it'll automatically find the next, and just keep going and going and for all the passes. That's the auto track feature. Well, I wanted the auto track feature and I wanted the feedback, but that I can't have both if I use the PC version. But I found out that the Linux Raspbian version, the version that runs on Raspberry Pi 3B, will use the latest version of gpredict, and it will give me the feedback, and it will give me the auto track feature. So that's why I ended up building this whole thing on a Raspberry Pi 3B. One is because it's in a small box that I can just kick around and it doesn't matter too much whether I break it because it's cheap. But two, it actually does all those features I wanted, the auto tracking and the feedback. So that's how I ended up with Raspberry Pi 3B as the PC. So the gpredict satellite will track the satellite of interest. It will throw out commands to the antenna controller, azimuth and elevation data that controls the antenna. It receives the feedback of where the antenna actually is in relation to those commands. Also, it will control the rig. It will tell the rig the uplink and downlink frequency. It will track the Doppler shift both on the uplink and downlink. It will lock the uplink and downlink together with a fixed offset. Makes it very easy for satellite contacts. And so I do both with the Raspberry Pi 3B. I have my, and you'll see here. Here's the overall system. Okay, you can have on PC or Raspberry Pi, the gpredict satellite. It has when you set up gpredict, it runs a little program, this application programming interface called Ham Library. Hamlib, it's Ham Radio Control Library, you've probably heard of that, it's free. And it basically takes the azimuth and elevation commands coming out of the gpredict software and translates those into CAT commands, which will run my FT857D transceiver. The API just calls up this RIG 122 profile, which basically means it's for the FT857D. And also it will then send out by the way, EasyCom 2 is an AMSAT protocol apparently. So Ham Library Profile 202 takes the commands to move the antenna controller, and that's the whole system. Basically, when you load up gpredict, you start the API. There are a couple of little programs. You just start them. They just run in the background. You don't really observe them. They then just they just move the commands as needed to and operate the radio and the antenna controller. Let's see. Let's see. Okay. So I told you I had to wait till March to test this thing out, and it took then. It was one afternoon. And I set this thing up on my deck using the setup I described there, and I gave I was listening out on CAS-4A, which is one of the transponder satellites that one with SSB, and heard KC9 TC calling CQ satellite, which is what you'll hear on the transponder satellites. And I gave him a call back. And immediately he came right back to me, gave my report, and we exchanged a few common courtesies, and said 7.3, and that was the contact. and that was my first true satellite contact. It was back in March this year, and it was very easy. I think it took me a little while to figure out how to use gpredict at first, but I think we fired this up, Dave, didn't we, on in field day and after midnight, and the first call we had, I called them back and we made a contact, first 100 points. So we met our goal. So that's the high level overview. I think we've got like 20 minutes to. We've probably got a lot of questions, and I deliberately didn't want to go through all the construction details and all. I mean, it's detailed enough, but everything you need is on the links that I've provided inside the presentation, how to build this thing for those that are interested. I really recommend this. First time I've ever done anything with Arduino, or even with anything with Raspberry Pi. So it was and the mechanics were interesting as well. One last mechanical point. There is a counterweight here that is basically a small metal box filled with lead weights from Walmart. And there's a little trial and error trying to get this. This is completely balanced. You can move this in any position. Obviously it doesn't move like this when it's really working. I tighten this thing up, but this is balanced. It's counterbalanced. Very important to reduce the strain on the motors. All right. Thank you.
Did you build the antenna or is that commercial?
This is commercial Arrow 2 antenna. Yep.
Eddie, can you comment on the learning curve for Raspberry Pi and also Arduino?
Okay. So I'll take the Raspberry Pi piece. I have never done anything with the Raspberry Pi. Like I said, first I was looking at maybe getting a laptop with Linux or something like that on it. I looked at the prices and I didn't want to spend $100 or more. To me it's fairly well. It's so public domain. It's so well documented. I mean, I bought the Raspberry Pi from Target. You open up the paperwork. It tells you where to go to download the basic software and everything. The steps are very well laid out. You just have to follow them and not guess them, right? As well as the steps to load gpredict on the Raspberry Pi 3B. How to load the actual the Raspbian software on it. The Raspberry Pi 3B also has Wi-Fi, which you use for the time updates. Right, it's very important for accurate satellite acquisition. Well, what happens if I'm in the middle of a field somewhere where I don't have Wi-Fi? So I ended up adding a real-time clock in there with this battery-powered real-time clock, and had to configure that. They're all add-ons, but I'd never done that before. And it's not something I do in my everyday job. It's not something I've done even in my past electronic lives 20 years ago. So I had to do it. Learn it from scratch. And then the other question you had was...
Same question with regards to the Arduino technology.
Yeah, the Arduino technology I'd never used before. But the details it's so detailed. The description from the SARC folks is that it talks you through about, of course you've got the circuit diagram with the connections, but it talks you through exactly what to do, in finite detail, and watch out for this and do this, and oh, by the way, if it doesn't do that, make sure there's a lot of, it was that easy, but you have to read through almost every line, check it and say, not applicable, yeah, I better make sure I do that. The whole issue about the noise, the interference that the device can cause, they were talking about, we attached, 0.1 microfarad capacitors on the I2C interface to reduce noise. It didn't do anything other than stop the I2C interface from working well. So I'm an electronics engineer. I googled it, but it turns out you can't have anything more than 400 picofarads across there. Otherwise, it flattens the square wave and the interface stops working. I found out 100 picofarads is perfect for eliminating noise in 2 meters with short leads. So it's experimentation. So it's a lot of fun. It was go ahead.
In that picture you had up just a little bit ago with the antenna, in fact,
Yeah.
That's were you operating outside, meaning the radio was close by?
Yep, yeah, the radio was set on the desk. Who was at Satellites in the Park? You guys saw this, right? I had my little Alinco DJ G5 HT that was actually sat on the desk. You can't see it here. In fact, that was the first time I ever operated battery. I operated this whole setup with the Raspberry Pi, the controller, and the monitor all on the battery. It was all on a 7 ampere hour battery. Like this, which I've since put in the box and put a solar controller on it now, so I can take that anywhere. Okay, go ahead.
Hi, Eddie. I have a question as to the radio you chose. With the ACU857, what made you choose that maybe as opposed to the 910? Did that come like
Well, a couple of... I actually bought this originally for mobile use, HF and VHF mobile use. Actually, that actually used to be my wife's truck, so she was elated when I took it out. But I like this radio because it's small form. It's very small, it's easy to put in. I have a little box, I have the whole thing in. Less smaller than that, it's just easy to be transported. But another thing is it just happened to be that the G-Predict software was specifically by accident. I found out the G-Predict software was specifically written with the FD857D in mind for satellite operation. Because Dave will tell you, I bought a IC9700 at Dayton this year, which I have in the shack.
You bought it for your wife, you said.
Which I bought for my wife when she gets it. Thank you. And
She gets a lot.
and it works. It doesn't work very well yet because the ham library, at least at the last time I downloaded, the ham library software isn't working quite so well with the IC9700 yet. However, we talked about Ham Radio Deluxe. It works beautifully with Ham Radio Deluxe. I can use Ham Radio Deluxe to send EasyCom commands to control the antenna and also to send the CATCOM commands to the IC9700, where it alternates between the uplink and downlink frequencies, but you don't hear anything. You don't hear any breakup in the audio. It's transparent. It works very nicely. So, tell a secret. Actually, I like using HRD really because I can use the 9700. But for rough and ready satellite outdoor use, I use this setup, the 857, because it fits in the box and it's a slightly cheaper radio than the other one, which I double the brake.
Yeah, when you're working satellite, one of the things that's not very obvious is one of the most important things is having a radio that's truly full duplex.
Yeah.
Especially when you're doing voice, because you really want to wear headphones and be able to ensure that you're actually making it into the satellite so you can hear yourself coming back on the download. Yeah. And the 857, the 817, 818 seem to be kind of like the de facto radios for satellite.
The good point about that is that if you use this, see, this radio isn't duplex. It's like it alternates. It's in receive mode all the time. Every 2 seconds, it will check whether the transmit's been active or not. So this radio is not duplex. But that doesn't matter because if you're tracking the uplink and downlink together, you don't have to worry about that. So go ahead.
I'm just curious, down here, the magnetic declination is only about 5 degrees, so we don't have to worry about it. But when I go up north, it's 15 degrees or more. Do you correct that in the Compass software or in the G-Predict software?
I don't recall there being a offset in G-Predict that I've ever used, but certainly in the software you can change the declination value and then recalibrate. Yeah, that's what that's for. Set the magnetic declination. Another question? Go ahead.
Do you have to set any hard stops or boundaries in it so that you don't overdrive your motors beyond whatever, like you don't drive your antenna to the ground or?
So the software will controls that, so it knows it can't go below the horizon. It knows it can't go around more than twice, because if it starts to go around more than twice, it's got like an unwind routine. That's a good question, actually. So yes, it's smart enough to know if it's tracked a satellite and ends up going past it more than once. So so these wires start to wrap round. It will go up. No, I'm going to go all the way back round again before I can then start. It'll do that.
So if your accelerometer fell off the boom, would bad things happen? Or?
Yeah, you can have a lot of fun with this, actually. But I'm literally, I mean, you could stand here, and if I moved it like that, the antenna would still move around, like as if it was still attached to the boom. Yes. Go ahead.
What keeps the Raspberry Pi's software up to date with satellite information?
What you say that Raspberry Pi, you mean the gPredict software's up, keep the gPredict software up to date with the satellite information, right?
But it's running on the Raspberry Pi.
Yes. But it downloads, the gPredict software will automatically download the latest two-line elements, or if I can spell it, the Keplerian elements, whenever it needs to, as well as the transponder information, the frequencies and the uses of the frequencies, which is very, very handy.
So like before you go to the field, you run it, and then I always use it something like 20 years ago. You run, get the clearings and all that before you left the house, then you go to the woods.
Yeah, I mean, you do it basically.
It's still good for a week.
Yeah.
Would you like a picture of your setup if that satellite's in the dark?
Do you have one?
Well, he had one.
There's a good video done by, I'm sorry, I forget his call sign. Brian. Oh, there he is.
There you go.
A bunch of people in the background saying, where is this guy?
Can you see how all the antennas are in all sorts of different directions? Yeah, it's like, no, it's over here. It's over here. Very good. Well, I hope, is there any more questions?
Are you going to plug it in?
No, I didn't bring the rest of it. I didn't know if I'd have time. I'm sorry. Go ahead. Let me see. I showed up, I think, and I had it up in like 10 minutes or something like that. It's like get the chair and table out, get the umbrella out. That took the longest part. It doesn't take long at all.
With the E-compass, it's auto zero, so you can just drop it and plug it in, and
Yeah.
it's ready.
I mean, I'd be happy to bring it back and do a another demo for folks at the back of the room. One of the next meetings for sure. I just wanted to more talk about the setup and the mechanics of this thing. But well, if there's no more questions, thank you so much for your time. And let's give a